Hello everyone, this is our notes video for section 5.5, solving trig equations. Right at the top of the notes, we have a little area there for just some strategies, right? We're not always going to solve these trig equations the same way. We're going to have to approach them. Different cases will require different, techniques. So here are some strategies. Isolating our function to one side of the equation and then using inverse operations, just like we would solve an equation in any other unit, right? Work backwards to isolate the variable. Factoring and solving will be helpful here. Graphing and finding intersections. And finally, using identities to simplify. We'll see some examples of each of these as we work our way through these problems. And, we will see a few examples of each, and then we can see what works and what doesn't in which situations. So let's take a look at our first example. We always want to pay attention to the domain over which we are solving our equations. In this case, we are solving from 0 to 2 pi. So as I look at this, I have 3 tangent squared x equals 1. And what I want to do is work to isolate the tangent x trig function. So I'm going to divide both sides by 3. And then take the square root of both sides. I'm going to rationalize this. We don't like that root 3 in the denominator. So I will get root 3 over 3. Again, that is a plus or minus there. And why that's helpful for us is that this shows up on our unit circle. So what we're really looking for are coordinates on our unit circle where the y over x, in other words, our tangent value, equals root 3 over 3. So as I work my way over here, I'm going to just kind of experiment. Let's see what works. If I were to look at, say, pi over 6, that would be y over x 1/2 divided by root 3 over 2. This is the same as 1 over root 3, which hopefully seems a little bit familiar. We saw that as an intermediate step as we were working. If we were to rationalize, we would find that the angle pi over 6 would work. Additionally, another angle would have the same ratio, right? If I'm dividing y over x, the first and the third quadrants are both going to result in a positive outcome. So we have 2 solutions here of pi over 6 and 7 pi over 6. Don't forget, though, we have a negative version of the same angles. The ratios are going to behave the same way. We just want the signs to flip. So in addition to pi over 6 and 7 pi over 6, we're going to include 5 pi over 6 and 11 pi over 6. Now, as far as tangent goes, this function has 2 complete periods over the solution interval here from 0 to 2 pi. So we see 2 different repeated values, right, that are pi units away from one another. Oh, sorry, I think I made a mistake on that. It should have been, there we go. 7 pi over 6 is pi units away from pi over 6, and 5 pi over 6 and 11 pi over 6 are pi units away. They're effectively related points at within different periods of the function. So here we have 4 solutions. Let's see what happens on example number 2. Here I have sine on both sides of my equation. So what I want to do here is I want to isolate sine as if it were, x, as if it were a variable. So I'm going to get negative 2 sine x on the left, and on the right I will have positive 1. I'm going to divide both sides by negative 2. So sine x will equal negative 1/2. Well, now I'm on my unit circle. So I'm going to go look at my unit circle. Where does sine of x equal negative 1/2? Well, that's going to happen in 2. Let's get rid of these marks from last problem. If I'm looking for a sine of negative 1/2, I'm looking for a y coordinate of negative 1/2. That happens in 2 places. That happens at 7 pi over 6 and 11 pi over 6. So our solutions are as simple as that. So x equals 7 pi over 6 and 11 pi over 6. This is a problem where we are isolating our trig function and then working backwards using inverse trig functions to evaluate for specific sign values. We can move on to 3. It's very important here to recognize kind of the shape of things, the structure of this equation. If you kind of squint, this looks quadratic, right? We could understand how that is related to quadratics. And if we were solving this problem in a quadratics unit, we would solve through factoring. Well, we can do the same thing here. Just some indicators, what maybe leads me to that idea of solving through factoring. Well, I have this quadratic shape, and the whole thing's set equal to 0. That's what we do when we solve. There's kind of a little breadcrumb there, a little hint as to where we might want to go. So in this problem, what's going to be different? Well, instead of just regular old x, the leading term in each of these binomials must be cosine x. So when if we were to distribute, we would generate that cosine squared x. From here, I need to find coefficients that are compatible with our linear and constant terms. That's going to be a -4 and a +1. Well, from here on out, we're using our zero product property. So we're trying to figure out when cosine x, plus 1 equals 0, or in other words, when cosine x equals -1. And then over here on the right, we're trying to figure out where cosine x equals 4. We can look for a long time, and we will not find a solution. There is no place where cosine of x equals 4. It is outside of our domain. It's actually outside of our range. So the only component here that's going to generate an answer is this one here, where we have cosine x equals -1. Cosine is the x coordinate on our unit circle. So where does the x coordinate equal -1? That happens over here. Our solution for this problem must be pi. And we have one more here that we'll take a closer look at. This one's a little bit tricky, and as you're looking at it, you want to be aware of what kind of makes it seem tricky. What I notice is that we have two different trig functions, that don't really interact very well with each other, right? Cosine and tangent. So what I'm going to do is I'm going to subtract 3 cosine x from both sides of my equation and factor a GCF. In this case, the GCF will be cosine x. We see it there and there. So when we factor out that cosine x, we're left with tangent x minus 3. So now, kind of the same situation we were in the previous problem. We have two factors set equal to 0. This is our zero product property. We need to figure out when does cosine x equal 0. On our unit circle, that happens in 2 places. Happens at pi over 2 and 3 pi over 2. These are not our only solutions here. We also need to figure out where tangent x equals 3. This is not something we are able to do from our calculator, from our unit circle. So instead, we need to use our calculator. So we would take our calculator, and we're really going to just use the inverse trig function, the inverse tangent function. We're trying to find an angle whose tangent is 3. That does exist. Remember, tangent has an infinite range, whereas sine and cosine are limited. So I'm plugging this into my calculator, and I find that x equals 1.25. Now remember, when we use tangent inverse in our calculator, we have a restricted domain, negative pi over 2 to pi over 2. So this answer, so that domain does not include our entire answer set. So just as we saw on example 1, where we had repeated solutions pi units away, on example 4, we're going to have the same thing. However, we're going to have to do this manually. So we're going to add pi to this. I'm just typing it into my calculator, and what we end up with is 4.39. So those two decimal solutions are the solutions that come from the tangent x equals 3. We need to add pi because tangent repeats in the unit circle. It has 2 complete periods in the unit circle. And the inverse tangent doesn't give us everything we need. We have to extrapolate a little bit from there. I'm going to go ahead and graph this and then kind of talk about the graph in just a moment. But I'm going to pause and graph it and just save ourselves some time. All right, with some movie magic there, now we have some a graph to take a look at. So they are trying to, we are trying to solve through graphing. We can solve a lot of trig equations through graphing. Oftentimes this will be in our calculator. But this graph in particular is worth looking at for a few reasons. First is the sign 2a. That 2a acts as a horizontal compression to our graph. So over the course of 0 to 2 pi, we will complete 2 complete periods. What this means is that the number of solutions that we have over the same interval from 0 to 2 pi is quite a bit more, right? Instead of having just 2 solutions, we now have 5 solutions, because in this case we're including the endpoints. So when we have a horizontal compression or any number in here that's acting upon our variable, it's going to change the number of our solutions. So that's one part of this. The other part of this is just the idea that if we get stuck and we are on a calculator type problem, you can always graph in our y equals, and well, in this case we would find x-intercepts. We could also graph a horizontal line if we had some decimal approximation that our equation was set equal to. So graphing is valuable. It's solving an equation through graphing is the same here as it would be in any other chapter. You're going to graph it and you're going to find either x-intercepts if our equation is set equal to 0, or intersections if we're setting 2 different equations equal to each other. Let's turn over to page 2 here, and we have a few more problems that we're going to solve. I think we have 5 remaining. I'm going to try to go a little bit quicker through these, but we'll have to demonstrate a few new techniques as well. Here, this one kind of appears pretty straightforward. We have 2 cosine 2x minus 1. So we add 1 and divide by 2. We get cosine 2x equals 1/2. That seems okay, except that this 2x is kind of a complication. So this is one thing we can do, is we can use something called U substitution, something you'll use more extensively next year in calculus, to just make this a little bit easier to work with. Cosine of u equals 1/2. Well, we know where the cosine of u equals 1/2. We know that 2x, or u, equals pi over 3, or 5 pi over 3. Well, remember what we saw in our graph. With that 2x, that cosine 2x, we have created a horizontal compression. All right, a horizontal compression in our graph. So this 2 tells us that we should have twice as many solutions. So we're going to go for a second rotation on the unit circle. All right, so what does that mean? I'm going to include possible solutions that actually do not exist currently on our unit circle. 7 pi over 3. And then additionally, 11 pi over 3. Now, I 100% agree these are not solutions that exist on our solution set. However, remember, these are all what 2x equals. So when we actually solve this, we're going to divide each of these fractions by 2. We get pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And after we divide by 2, we can see that all of these solutions are valid. They exist on our interval because we had to divide those extra values by 2. We can move over to 6, and we're going to see something a little bit similar. What I really like about number 6 is how it forces us to notice structure. I would say without trig identities, something like sine x times cosine x gets a little bit tricky. We saw an example, I believe it was example 4, where we did some factoring, right, with some similar values here, but we can't really do much here. So what we do instead is we write this as 2 times sine x cosine x And the reason we would do that is because what we've created here is the double angle sine formula. So this 2 will still be present, but we can replace 2 sine x cosine x with sine of 2x. Now this problem has become pretty similar to our previous problem. We divide both sides by 2. So sine of 2x is root 3 over 2. Some people don't love u substitution, so let me just show you what it would look like if we didn't use u substitution. We would say that 2x equals, well, I'm thinking about sine values where the result is root 3 over 2. That's the top half of my unit circle. That's going to happen at pi over 3 and 2 pi over 3. Remember, this 2 here tells me I need to go around the unit circle a second time. So I'm also going to include a coterminal angle with each of these. Coterminal with pi over 3 will be 7 pi over 3. And coterminal with 2 pi over 3 is 8 pi over 3. Now our next step, we're going to divide everything by 2 to find what x is. That's going to be pi over 6, pi over 3, 7 pi over 6, and 4 pi over 3. Again, even though we included 2 answers, kind of temporary answers that were outside of our solution set, when we divide them by 2, they end up back into our unit circle answers, our solution set of 0 to 2 pi. All right, so there's a couple more problems here that we're going to solve similarly. However, in these problems, we are not going to have domain restrictions. All solutions must be found. So we know with trig functions, these are infinitely repeating, so we're going to have an infinite number of solutions, but we can be more specific than that. So we're going to approach this, as we look at this, what can we do? What I'm noticing here is sine 2x. So I'm going to use sine 2x. I'm going to use the double angle identity. Why am I writing it backwards? 2 sine x cosine x equals 0. What about that? This problem led me to that. Again, whenever things are set equal to 0, I want to try to factor. And I know that I can rewrite sine 2x as 2 sine x cosine x, so that 2 cosine x is factorable from both terms. So that's what I'm going to do. I'm going to factor out 2 cosine x. I'll be left with 1 plus sine x. So now we're going to solve the same way we've been solving. Where does cosine x equal 0? Well, we know that happens in 2 locations on our unit circle. And if we were to continue that set of numbers, it would be, 5 pi over 2, 7 pi over 2, right? And this can be valuable just to identify the pattern of our solutions. Similarly, we want to figure out where sine x equals -1. Well, that's going to happen when x is 3 pi over 2. It would also happen at 7 pi over 2. Well, for this problem, we need to find a way to express all of these solutions here. Right, we've listed out a few of them, right? 4 on the first one and then 2 on the second. But we can be more specific than that. We can say that the set of numbers that represent our solution, well, they start at pi over 2, and then we add some multiple of pi. So the way we would write this is x equals pi over 2 plus pi n. Now, on some problems, we may need a second solution set, but if we look at our set of blue numbers here, these numbers are already embedded and included in this set of solutions, so it's not necessary to include their solutions as well. All we need is this solution set here, pi over 2 plus pi times n. All right, let's look at another one. Here we have tangent of 3x equals 1. So this is going to be a direct solution here. This is maybe a solution where it's actually maybe easier to write our solution set for all solutions as opposed to specific solutions over 0 to 2 pi. So if I have tangent 3x, the period for this function would be pi over 3. So over the course of 2 pi, we would have, 6 solutions. Over the course of 0 to 2 pi, we would have 3 solutions because there's 3 periods included. But let's take a look at where we go. So where does tangent, we can use u substitution here. Let's say u equals 3x just to clean things up. Tangent of u equals 1. So I'm thinking about my unit circle. I'm thinking about where those values of tangent equal 1. That happens at pi over 4, and it also happens at 5 pi over 4. The next solution would be 9 pi over 4. The solution after that, 13 pi over 4. I like to include a couple extra values just to kind of confirm what you notice about the pattern in the solutions. So we know that u is actually the same as 3x. So if I actually want to find x, I'm going to have pi over 12, 5 pi over 12. Let's see, 9 pi over 12 is 3 pi over 4, and 13 pi over 12. So what's the pattern? Well, to go from pi over 12 to 5 pi over 12, I'm adding pi over 3, which seems familiar. Same thing here, I'm adding pi over 3. Again, adding pi over 3. So the way we would write our solution set is that x equals pi over 12 plus pi over 3n. And there we are. The last problem is a little bit more complicated, but I think that we've seen enough that I'd like you to try it on your own. I'm going to work it out and then quickly explain my work in just a minute. All right, everyone, appreciate you hanging in there on this video, a little bit on the longer side. So let's take a look. So my first step here, I need to deal with the fact that we have sine squared and cosine x. Those are not really compatible for us if we want to solve through factoring. So what I did is I used my Pythagorean identity to replace sine squared with 1 minus cosine squared. I distributed that 2 in and moved everything to the other side of the equation so that I had a positive leading coefficient of 2, and then I factored. As you can see here, I have 2 cosine x minus 1 times cosine x minus 1. I end up again, kind of a familiar territory here. We have some repeating solutions. And what I want to just pay attention to here is the interval between our solutions. Right? I have these color-coded differently because these are irregular intervals. We're not adding the same amount every time. So because we have irregular intervals, we may need more than one solution set. So here you can see our pattern goes, let's grab a new color here just for some variety. We have pi over 3 and 7 pi over 3. Those are separated by 2 pi. They are represented by this part of our solution. To go from pi over 3 to 5 pi over 3, that's 4 pi over 3. And then to go to the next term, it's 2 pi over 3, right? Again, we're not balanced. So we need to be careful there. That 13 pi over 3 doesn't seem to make sense there. Let me fix that. I think I did some miscalculating there. So if we wanted to go 2 pi up from 5 pi over 3, that would be 11 pi over 3. That seems a little bit better. So just to finish this up, these are our solutions. We end up with pi over 3 plus 2 pi n. This, what you see circled in pink, is one of our solutions. Then we have 5 pi over 3 plus 2 pi is 11 pi over 3. Our next one would be 17 pi over 3. They are represented by this form of our solution, 5 pi over 3 plus 2 pi n. And then finally, we also have this third set of solutions coming from cosine x equals 1. There, our solutions are 0, 2 pi, 4 pi. They are represented by a third set of numbers represented by 2 pi n. Realizing I may not have mentioned this earlier, that n is representing any integer value. N is an integer. So any integer can get plugged in for n, and it would represent one of a possible solutions to the trig function. That's all for today. Thanks, everybody.